So we begin chapter 11 by introducing the whole zoo of particles, as we say. We're going to take a look at the most fundamental particles in nature. And what we're going to notice is some of the most fundamental particles in nature don't include familiar particles such as protons and neutrons. When we say the word fundamental, we're talking about particles that we don't believe that we can divide into any smaller pieces. And we know that the protons and neutrons are actually composed of quarks. So what we're going to present here are just fundamental particles, particles which are the most simple unit of whatever we're looking at. So let's start out, first of all, by introducing or reintroducing, really, the different forces of nature. We know, of course, there's a strong force, which is responsible for holding the nucleus together, holding quarks together to form protons and neutrons. We have the electromagnetic force, which allows interactions between charged particles. We know with the protons in the nucleus, we saw that this reduced the binding energy because it was a repulsive force, but it's also the force responsible for holding the atom together. Electrons orbit the positive nucleus due to the attractive force between the charges of the electrons and the positive charge of the nucleus. Of course, we have the weak force, which was very important in our discussion of radioactive decay, especially beta decay. We saw that the weak force played a role there. And then, of course, gravity is the first force that we always study in nature. We always study in physics. Gravity is the weakest of the fundamental forces by mass. I guess that's sort of irony if you want to analyze that statement. But again, strong force, it is the force that is caused by the boson we'll talk about a little bit later. It's called the gluon. And essentially, the protons and neutrons will give off virtual particles, which create an attractive force, but the attractive force is very, very limited in distance. The protons and neutrons are held together by the gluons, and then there are actually virtual, what we call pions, which create the interaction between the protons and the neutrons, holding them together. But again, strong force is what we know to hold together the nucleus. The electromagnetic force, going back to our classical understanding of it, comes from Maxwell's equation. It was very, very important for when we talked about the wave equation for light. And of course, if we combine Maxwell's equations, we do get the wave equation for the electromagnetic waves. The weak force, kind of a different force from what we've understood forces to be. With gravity, we understood that gravity was always an attractive force between objects with mass. With the strong force, we soon learned that this is what created the attractive force holding the nucleus together. And of course, with the electromagnetic force, very, very important for holding the electron bound to the atom. But now we have a force that doesn't always behave like a force. Yes, it actually does have the ability to push or pull, but that's not really where we typically see an interaction with the weak force or with the weak interaction. Typically, what we see is that the weak interaction allows for instance, quark to change from an up quark to a down quark. This allows a proton to be converted to a neutron. And when this happens, electron is absorbed and a neutrino is given off. This is actually the case of what we call electron capture, which is mediated by a W- particle. But again, the weak force is going to be very, very important because it's going to allow the quarks to actually change what type they are. Again, very, very short range, the weak force. It's most dominant at a range of about 10 to the minus 18 meters. It does extend, beyond that. It actually does have a range which can be as large as 10 to the minus 15 meters. But unlike the strong force, it has a very strong cutoff. Really, by the time you're getting that far away, the weak force really doesn't have the same influence. So the weak force, again, very, very small range, which means that interactions via the weak force are not very common. while the strong force is always holding the nucleus together, it is very uncommon for a beta decay to happen, and we'll get into more about that later on. Neutrinos are particles that are only affected by the weak force, so that when a neutrino is detected, and neutrinos are detected by these very, very large detectors, sometimes filled with heavy water, sometimes with other types of materials that make it easy to convert the energy of the neutrino to something that's visible. But neutrinos are ghostly particles. You see, they pass through things so easily that when we have trillions of neutrinos passing through an object, it's very rare that even one will interact, and that's through the weak force, that it can interact with perhaps a particle in a nucleus, give the nucleus some energy that'll transfer to its electronic energies, and we can see it as a flash of light. Again, here we see a neutrino colliding with a nucleus, transferring its energy. But again, the weak force very rarely does this. We can think about, in terms of cross-section, the likelihood of this interaction taking place as the neutrino comes near the nucleus is very, very small due to its small interaction distance. Don't need to say very much about gravity. As we said before, gravity, anything with mass, is attracted by anything else with mass. It is mediated by the what we believe to be, if quantum gravity does really work, a particle called the graviton. Of course, when we talked about general relativity in this course, we saw that general relativity saw the gravitational force as being a curvature in space-time, and that objects move not because they were being pushed or pulled necessarily, but because they were going along a trajectory which was took the least amount of time in all four dimensions, going along with the principle of least actions. Okay, so let's get back to particles, because that's really what this section is. We're introducing these fundamental particles, and we're going to have to classify them different ways. Now, the first way we can classify them is by spin. And why do we care how this object is spinning on its axis? Well, it's actually not that simple, and it's actually a little more important than it sounds. The particle's not actually spinning per se, just like the electron's not actually orbiting the nucleus of the atom. The spin is very much a classical property. But on the quantum mechanical side, when we look at the wave function of the particle, it does contain angular momentum to it. Okay, so two ways we classify particles according to spin. We can either classify them as being a half integer spin, or we can classify them as being a whole integer spin. Half integer spin particles are called fermions. Whole integer spin are bosons. Now, when we're talking about spin, the actual spin, or the angular momentum due to the spin, or what would be the classical analogy, that angular momentum is 1/2 h bar, 3/2 h bar, 5/2 h bar, so on or so forth. Okay, most fermions, almost all the fermions that I can think of that are fairly common, have spin 1/2. Okay, so yes, they can have spin 3/2, 5/2, and so on, but at least for the fundamental particles, they're almost all spin 1/2. Okay, now this leads to a very, very important rule, and fermions include electrons, protons, neutrons, quarks. They can't have the same wave function. This is called the Pauli exclusion principle, and it says that no two fermions can have the same wave function, and oftentimes, because the energy is associated with the wave function, we saw this when we talked about the energy operator, the energy is an eigenfunction of this. We can't have two electrons exactly in the same orbital. Okay, chemistry, we talk about the wave functions in terms of orbitals. Like in the first, the n equals 1, the principal quantum number n equals 1, you can have a spin up or spin down. The angular momentum quantum number L is 0 in that case. For the next shell, n equals 2, we can have an S or we can have a P. The S also is spin up, spin down. If the P's, there's actually 3. You can have a spin up, spin down, spin up, spin down, spin up, spin down. But what we see here is when we start filling out the periodic table, no two electrons can occupy the same wave function, can have the same orbital, have all the same quantum numbers, really, right? Can all have the same N, L, ML, and MS. Okay? And that's a reality for any of these spin 1/2 particles. We saw it when we looked at the shell model for the nucleus, that we'd have a spin up and spin down proton, spin up and spin down neutron, occupying different energies within the nucleus itself. So again, very, very important. Pauli exclusion principle. And when we talked about fusion, I even mentioned this idea of degeneracy pressure. Degeneracy pressure is the fermions getting closer and closer together, but the wave functions can't overlap. And because of this, you actually have this repulsive force between them, which is a very, very powerful force that prevents further collapse. In any case, bosons, they don't care. They can all have the same energy state. And a boson typically is going to be a particle with spin 0 or spin 1. The exclusion principle does not apply to them, and that's very important in terms of superconductors. Superconductors actually have composite particles. You have an electron and would spin up and an electron would spin down, which are bound by vibrations known as phonons. And the composite particle by itself has spin 0. And therefore, these composite particles can occupy all the same energy level. Now, typically, in a regular conductor, because the electrons are acting like independent particles, fermions, you have to occupy all different energy levels, and thus their wave functions make them interact with defects or different parts of the lattice, or even vibrations in the lattice. When something goes superconductive, some of the electrons pair up in what are known as these Cooper pairs. They're bosons. They occupy a very low energy level where their wave length is very, very large, and therefore they don't interact with crystal defects or even other vibrations there, and they don't give up any resistance. So superconductivity is a purely quantum mechanical phenomena. And basically, just because the particles can combine their spins together to produce a 0 spin, this allows them to behave differently from the normal way that conduction electrons behave. Okay, enough of that. Superconductors, superfluids, the different particles team up together to become bosons. Now, let's get to some other ways we can classify particles. We saw half integer spin allows us to classify something as either a fermion, or if it has a whole integer spin, a boson. Spin is very, very important because there are different rules for fermions, different rules for bosons. Now, there's also some particles that interact only via, I should say, there are other particles that interact via the strong force, where things like leptons, which we'll talk about in a little bit, do not interact via the strong force. For instance, electrons can't interact via the strong force, so they are not hadrons. Protons, neutrons interact via the strong force. Muons, pions, kaons, these are particles which are made of quarks that also interact via the strong force. Basically, for the strong force, it's normally quarks and gluons which only interact by this very special force. And again, that's why protons and neutrons are bound within the nucleus, but we don't have other particles bound in there, such as electrons or more exotic particles like muons. In terms of the hadrons, we've got the big boy particles, the baryons. These are composed of 3 quarks. And when we talk about quarks, we're going to talk about color charge. There are actually 3 different nuclear charges. It has nothing to do with electrical charge. The electrical charge is something completely different. But these nuclear charges, instead of a positive and negative, we have what we call colors. No, they don't actually have colors, but they figured with the 3 primary colors, we can come up with sort of an equivalent. When all 3 primary colors, red, green, and blue, are added together, they produce white. That's the way we look at this color charge. That there are 3 charges here that we need to neutralize the nuclear charge. And that's why 3 quarks come together to produce a proton, 3 quarks come together to produce a neutron. So baryons are the heavy ones. We think about, these particles. The baryons are 3 matter quarks. We'll talk about antibaryons, which are made of 3 antimatter quarks. Meson is derived from the idea of middle. Okay, so a meson is a middleweight particle. They're typically a little bit heavier than leptons, but they're also lighter than baryons. Mesons are made of a quark and antiquark pair, which seems strange, right? Quark and antiquark pair, you'd think that matter and antimatter would annihilate, but they're not always a particle with its antiparticle. Some are, most are not. They're maybe an up quark and an anti-down, or a down quark and an anti-up. But these quark-antiquark pairs usually make them less stable, and they typically decay, as we saw. The pi meson is the particle which is typically exchanged by protons and neutrons that help hold them together via the strong force. So baryons, the big ones, mesons, the middleweight ones, these are all made of quarks. These are all hadrons because they interact via the strong force. Leptons are particles that, in general, just do not feel the strong force. Okay, and what do we know to be a lepton? Electron is probably the most famous of the leptons, but we also have muons, tauons, and neutrinos. Did I call a muon? Didn't I? The muon is not meson. Oh, let's go back here. I don't know why I said a muon was a meson. Pion is a meson. Hey, it's a zoo. Sometimes I lose track of all the animals. Pion is a meson. A kaon is a meson. Terrible, terrible, terrible. Muons are leptons. So in any case, electrons are a type of lepton. Electrons are a type of lepton. Muons are a type of lepton. Muons will decay into particles, including electrons. Tauons are even heavier, and neutrinos, of course, are the lightest. Okay, they do not interact via the strong force. And neutrinos have no charge. The electron, muon, and tauon, they do have charges. Okay, let's talk about antimatter, because I keep bringing up antimatter, and you've seen enough of antimatter in science fiction. We're going to talk about antimatter here in terms of what really happens on, in the universe. When we get into the very early epochs of the universe, we're going to talk about the production of matter and antimatter and how most of it annihilated and a little matter was left over. But we can think about antimatter in a number of different ways. And there's a very appealing model that I'm going to talk about in just a little bit. But with a very intense gamma ray, if it is under the correct situation, normally it needs a nucleus to give up some of its momentum to. A gamma ray can become a positron-electron pair, electron-positron pair. And essentially what happens here is every time we take energy and we turn energy into matter, we have to create an equal amount of antimatter. The basic rule of thumb is an antiparticle is going to have all the same properties as its matter counterpart, but things will be reversed. Like an electron and a positron will have opposite charges, equal and opposite charges. An electron and a positron will have opposite spins, things like that. And of course, when a particle of matter and a particle of antimatter of the same type come together, they come together and they annihilate, usually just generating energy in the form of photons. Now, where did we first see antimatter? Well, the first place that we saw antimatter was in beta plus decay, where a positron was given off. But it really wasn't quite understood what this positron really was. Give you a little background history. Early on, after the Schrodinger equation had been developed, a number of different physicists and mathematicians attempted to incorporate relativity into it. And, most were unsuccessful, but Paul Dirac, who was absolutely brilliant, figured out a way to merge both the de Broglie concept of this matter wave with relativity, and he came up with what is now known as the Dirac equation. Now, this is a very difficult equation. This gamma is not the same gamma that we used before. It's actually a matrix, and this derivative right here represents a four vector derivative. I guess a derivative in x, y, z, and time, because we know in general relativity we're treating everything in 4 dimensions. Well, that's my extent of what I feel comfortable explaining in terms of the Dirac equation. But if you remember in relativity, we saw how energy, E squared, was equal to the rest energy squared plus momentum squared times the speed of light squared. So we had this E squared, and we needed to take a square root on both sides. When you take a square root, you get a result with a plus or a minus. So here was a weird thing. I'm really oversimplifying the situation. But when we looked at the solution for this Dirac equation, what we saw was there was a solution for the electron, okay, which had a positive energy, but we also had a negative energy solution. And Dirac struggled with this for quite a while. He thought that, if we didn't have, some ground state that was filled up, the electron would drop down to, a state of zero energy, would spiral into the atom. So we imagine that, you had, because we're dealing with fermions, all these electrons, which are filling a ground state, and then this excited electron, which would be in an excited state, and a positron, which would be, analogous to a hole in a semiconductor. Now, that's not exactly what happened, and we're getting into quantum field theory, which is a whole circus to itself. But one can imagine that there exists these particle fields. There exists a particle field, perhaps for every type of matter, antimatter pair, and that we can imagine that this particle field, rather than the sea of electrons in this zero energy state, this particle field is constantly oscillating. Maybe we have some virtual particles popping in and out of existence, but basically, an electron, the way that this is viewed, would be like an excitation. Okay. After all, what is an electron? It's a matter wave. It's this oscillation of electric field and magnetic field in space. So if we add enough energy to this particle field and promote this electron, basically excitation, up to this positive energy, and we get this hole, or positron, going in the opposite direction, this is actually our matter antimatter pair. And again, we can't just suddenly have the electron pop out of nowhere, because by the Heisenberg uncertainty principle, that energy has to be paid back. So again, if one can imagine, very, very oversimplified, one can imagine a gamma ray coming in here, transferring energy or creating this excitation in this particle field and generating an electron-positron pair. And likewise, we would have the same for quarks, okay? That we could create a quark and anti-quark pair. And quarks can be put together to produce protons and neutrons. Anti-quarks can be put together to produce antiprotons and antineutrons. But again, this particle field is essentially, by this model, and this is just a model, seen as this thing that we can create excitations, and the excitations are basically particles. Okay, let's go into the standard model. Standard model is basically what we think are all the fundamental particles in the universe. And for all the particles that we see here, we actually have antiparticles. By the way, you can't see the photon because my little video covers this, but the photon is its own antiparticle, and some of these particles are their own antiparticle. Okay, but essentially with these particles, we have our leptons over here. I'm sorry, leptons down here. We have our fermions over here. Okay, we've got the quarks up here. Okay, which are the particles that interact via the strong force, and the leptons down here, which are particles that do not interact by the strong force. All right. Of the quarks up, down, these make up the proton and the neutron. And then you have more exotics like charm, strange, top, and bottom. Don't worry, we'll go into those more later on. Down here, we have the electron, the muon, which I called the meson before. Sorry about that. It's not, it's a lepton. The tauon, or the tau. And then we have the different neutrinos, the electron neutrino, the mu neutrino, and the tau neutrino. Over on the right, in the red, we have the particles that are associated with a strong force. Let's say the gamma ray. The photon, gamma rays are photons, but not all photons are gamma rays. We have the photon, the gluon, the Z particle, and the W particles. So there's 6 quarks, 6 electrons, 4 bosons plus one more boson we'll talk about at the end, which is the Higgs boson. Now, again, some models will predict even more particles than what you see here. They're supersymmetric particles, which are associated with a special theory known as supersymmetry. We don't talk about them here because they haven't been proven, they haven't been discovered. All the particles we see here, they've actually been discovered. So start out with the quarks. Up, down, scope. Up, down, charm, strange. I was going to say tau. Top and bottom. There's 6 types of quarks. Only 2 of them are stable over a long period of time. They were all formed very early on in the universe, but through the weak force, the top, bottom, charm, and strange quarks pretty much all decayed down to the up and down quarks. The heavier the quark, the less stable it is. So your heaviest quarks at the top here are going to decay the fastest. All right. Now, looking at their masses, it's very common for us to list the mass of these particles, not in terms of kilograms, but rather in terms of their energy with respect to electron volts. So what we have here is M for mega electron volts and G for giga electron volts. This is 1,000,000 electron volts and 1,000,000,000 electron volts. Okay, so let's put things in perspective. The electron has a mass of 0.511 mega electron volts. So it has half of a mega electron volt in terms of its mass. Protons and neutrons, you're going to see how fast you catch this. Protons and neutrons are approximately 2,000 times larger. Okay, so their energy is somewhere around 1 gigaelectron volt. Now, if I add up the mass of 2 up quarks and 1 down quark, I will not get the mass of a proton. All right? It's much more complicated than that because inside the proton, there's a whole lot of other things that are going on, which adds to the mass. It's very strange in our zoo of particles. But again, the up quark is the lightest at 2.4 mega electron volts. Then you have the down quark at 4.8 mega electron volts. Then the strange quark, this is the first quark other than the up and down quark to be discovered. And it had, as you might guess, unusual properties, thus the name strange. So that's at 104 mega electron volts, and that's significantly more massive than the up and down quark. Okay, the charm quark, even larger, okay, approximately 12 times more massive than the strange quark. So the masses get rather large rather quickly as we go to some of the higher energy quarks. The bottom quark is the next quark at 4.2 giga electron volts, and then finally the top quark at 171 giga electron volts. All right. So these are the different quarks. We put 3 of them together, we have a baryon. We put one of these and an anti-quark together, we have a meson. And we group them in generations. This first column here is known as generation 1. These are the particles that we're most likely going to find today. Up and down quarks make protons and neutrons. Electrons, we don't have to say much more about the electron. Okay. And then the next generation typically talks about particles which are not stable that have larger energies. And then the third generation, even larger energies. So again, we'll get into these 6 quarks, but again, if I put them on a logarithmic scale, you can see the up and the down quark, they're off by about a factor of 2. That's about as close as it gets. Okay, we jump to strange, 104 mega electron volts. We jump to charm, now we're in the, over 1,000 mega electron volts. Bottom, 4,000, and then top quark at 171 mega electron volt, 171,000 mega electron volts, 171 gigaelectron volts. Okay, so that is the different masses of these quarks, and it really is quite amazing to see how the mass changes by orders of magnitude as we go from the first generation, the second generation, to the third generation. And again, for every quark, there's an anti-quark. The up quarks have plus 2/3. The down quark has negative 1/3. That's why if we have an up, up, down, okay, we have a total charge of +1. That is the proton. Okay, if we have a down, down, up, then that is 0 there. And again, charm is sort of like a heavy up quark. Top is like an even heavier up or charm quark. And then again, strange goes to down, and bottom goes to down also. All of these, again, they're all fermions. You all have spin 1/2. The leptons are down here, and at the top here we have the neutrinos, the electron neutrino, the muon neutrino, the tauon neutrino, or I should say the electron neutrino, the mu neutrino, the tau neutrino. The electron, we're familiar with the electron. Again, about 0.5 megaelectron volt of mass, but the muon has all the same properties, just much heavier. Same thing with the tauon, all the same properties, just a lot heavier. Okay, and again, we go from 1/2 of MeV to over 100 MeVs. Okay, so a muon is a really heavy electron at 200 times more massive. And then we go up to the tauon, get ready to do some math here, in terms of, 3,500 times more massive than the electron. These are very, very impressive particles in terms of the total mass. 1.7 gigaelectron volts, if you will. It's very close in mass to the charm quark, where the muon is very close in mass to the strange quark, in any case. And again, you can see here's the electron. This is a logarithmic scale. So, we're going up to less than 1, greater than 100, greater than 1,000. And again, 6 basic leptons and anti-leptons, or particles and antiparticles. The electron has a positron as its antiparticle. The electron neutrino has an anti-electron neutrino as its particle. The muon has the anti-muon as its particle, so on and so forth. All right. By the way, we don't know the mass of the neutrinos. We think the neutrinos are probably on the order of a few EVs, but in order to detect them, we have to collide them with much more massive particles, and due to conservation of momentum laws, it's very difficult to get their exact mass based on the types of collisions. But again, we think these neutrinos are not completely massless. That's important because if they were massless, they could travel at the speed of light, that they do have a little bit of mass, maybe in terms of a few EVs, but really, really light. They make the electron look bulky. Finally, the bosons are over here, and my face is blocking our photon. But each of these is responsible for transmitting one of the fundamental forces. I have no mass for the photon and the gluon because, well, they have no mass. The photon has no mass, it has no charge, so it's just an electromagnetic vibration. The gluon is also massless, but it carries color charge. So that's going to have very important implications, and we'll talk about that later, meaning that gluons are actually feeling self-force from the strong force. They are attracted by the strong force as well as they carry the strong force. The Z and the W particles are the carriers of the weak force. The Z0 has no charge. The W plus and W minus have charges, which are indicated by their sign there. Okay, so Z particle about 91.2 gigaelectron volts, the W particle about 80.4 gigaelectron volts. So these particles are more massive than all but the top quark. Okay. Now, great, I'm blocking it. There's a particle hanging out behind my video called the Higgs boson, and this has a mass of 125 gigaelectron volts, so it is just slightly less massive than the top quark. It produces something we call the Higgs field. It's a hypothetical field that is responsible for giving particles mass. And again, to be quite honest, it's well beyond the scope of my ability to explain well or the scope of this course. So we're going to just say that the Higgs boson is the carrier of the Higgs field. And again, when we put all the particles next to each other, we see that the Higgs particle is quite massive. And again, electron is the lightest on this chart. We haven't shown neutrinos. Neutrinos would be the lightest if we could show them, but we don't have their exact mass. So it would go neutrinos, electron, up quark, down quark. These are the three particles with mass, which are common now in our universe. Of course, the neutrino and the neutrino and the photon, as well as the gluon, are also very, very common, but they have no mass. We have the strange quark, the muon, the charm quark, the tau meson or tauon. The bottom quark, W and Z, are very close in weight to the Higgs, and then finally the top quark is the most massive. So once again, that's just introducing you to these particles. We haven't said very much, other than we said there are different rules for fermions and bosons. We also said that if a particle experiences the strong force, it is what we call a hadron. Okay. In terms of the leptons, they do not experience the strong force, and particles like the neutrino, because they're neutral in charge, have a very difficult time interacting with anything. If something is charged, it's going to interact through the electromagnetic force. Okay. All right. Well, that wraps it up, and that is your zoo.